So we can conclude maybe mini batch HCD is one of the major ideas to do any kind of the optimization algorithm for larger data sets also. So that is a conclusion I can say for the mini batch HCD, taking instead of taking some of the all the points, but taking only for the few of the points with respect to the mini batch HCD. But one of the disadvantage with respect to the mini batch HCD also. So what will happen eventually? Let's go and see this kind of the plot. So in the gradient descent, you can see in the gradient descent, we are directly computing the all the different weights corresponding very sequentially. You can say very sequentially. We are just compute to get the minimal loss results. So this is the minimum loss results we are going to be get at the end. So we are just computing the sequentially. But what will happen in the mini batch HZD? They are observed some of the little trick. We are also little go and see the how does that going to be helpful in the IPython notebook. So what will happen with eventually gradient descent is this a sequential in nature. Sequential in nature, it may not be create the noisy. It may not be create the noisy. It is a denoise kind of the thing. But if you directly use the gradient descent, it takes a lot of the time. This takes a lot of the time. So that's the reason we are using as a mini batch HZD. What will happen with respect to the mini batch HZD? So let's look on this one. You can see here. You can see here in this plot somehow the typical nature of the stochastic gradient descent is slightly waving out. So let's remove this movement out as for now. So what will happen in the typical nature of the stochastic gradient descent SGD? It's somehow movement out. So it will going to be create some noisy kind of the thing with respect to the weights. They will create the noisy kind of the thing with respect to the waste. So this is also one of the disadvantages in the stochastic gradient descent. Disadvantage with respect to the stochastic mini batch stochastic gradient descent, you can say stochastic gradient descent. So what will happen in the stochastic gradient descent having the disadvantage of the noisy data or noisy weights are going to be updated not smoothly. So you have to denoise the data for that matter. Denoise the data. So for the denoise the data, we have another algorithm called which is very popular or very you can say another algorithm called adder delta. So we can also use something other information before going to the adder delta is momentum. So momentum is going to be very helpful to denoising your data. Denoising your data. So what will happen? The momentum it's going to be slightly correlated with it. And suppose you have a computation weights nu w is equal to w old minus. So I will write something called as a neta times. This is called as a learning rate with corresponding to dl by dw with old one. So yeah, old one. Old updated weights. So what will happen eventually? I will given something called as a neta times. So it will somehow denoising the data. Somehow denoising the data. It will eventually helpful. It will be in the range of 0,1, 0 to 1. If suppose you can take 0.01, it's somehow to smooth or it's somehow to remove the noisiness in the curve or in the momentum. So for that I will use as a neta. So this is the optimization equation or updated weight function corresponding to whatever we learned in the gradient descent. So let's go and jump onto the other algorithm called adder delta. So adder delta is for just slightly extension to whatever we learned up to the momentum SGD with momentum. You can say SGD with momentum. So adder delta, which going to be tells us instead of taking neta as a constant for all the updated weights, what if I will take different neta values for different weights. So that's how it's going to be very helpful. What if I'm going to be take the neta values as going to be not constant and different values are going to be updated with respect to the each and every weight. So for that, why we are using, I mean, what is the basic idea to use as each and every weight means? You may be probably having the futures sparseness. Okay, sparseness. Sparseness is nothing but most values are very zeros, very close to zeros, or very zeros, you can say very zeros. Further, we're going to be use these kind of the sparse matrices as some of the weight are not updating properly in your neural network at a time, so that you will be encounter with zero kind of the updation with corresponding any multiplication you will take with the zeros, that is zero only, right? At the time you multiplied with so many zeros, it may not be learned so many features or so many patterns according to your model data sets functionalities results. So further, we are not using that much of learning rate as a constant concept in the other delta. We are just slightly correlated to understand why, if what if we're going to take the different values for the different updated weights is going to be consideration. So that is the one good method to implement in the other delta. It will be works well when compared to the SGD with the momentum. And one disadvantage with the other delta also. Okay, so one disadvantage with the other delta also, that consists of what if taking the learning rate differently, that is fine, but what if I will take some neta value, that is a new updated neta value with corresponding to the neta of the formula is going to be looks like the updated the neta with different weights alpha of t to the power of -1 plus some approximation, you can say. So I will also tell you what is alpha t minus 1. So what will happen with respect to this new updated neta times. So I will write the equation like this, right? W volt, sorry, W new is equal to W volt minus neta slash derivative of dl by dw with respect